EVPN-VXLAN reference architecture module. By the end of this module, you should be able to describe EVPN-VXLAN reference architectures. The three Ethernet VPN Virtual Extensible LAN or EVPN-VXLAN reference architectures that you learn about in this module are displayed. The bridged overlay architecture is a fabric design, which Ethernet bridging occurs between the leaf devices through VXLAN tunnels being formed between each leaf device. This architecture works well for legacy networks that must support EVPN-VXLAN, but it struggles with facilitating inter-VLAN communication. All inter-VLAN communication must go through an external Layer 3 device, which is not an efficient use of resources and adds latency to east-west traffic. You can refer to the Juniper Pathfinder website for the current list of devices that support bridged overlay. You can access the link from the reference links document in the resources section. Centrally routed bridging, or CRB, is a fabric design that is similar to the BO design, where Ethernet bridging occurs between the leaf devices through VXLAN tunnels being formed between each leaf device. However, inter-VLAN traffic is not required to leave the fabric. Routing occurs at the spine devices, which are called Layer 3 VXLAN gateways. These spines have integrated routing and bridging, or IRB, interfaces that route the traffic between VLANs, which enables better resource utilization and lower latency for east-west traffic than the BO design. The spine devices have IRB interfaces that route the traffic between VLANs, which enables better resource utilization and lower latency for east-west traffic than the BO design. The CRB design is not as efficient as the ERB design, but the configuration of the CRB design is simpler than the configuration of the ERB design. The ERB architecture is a fabric design that is similar to the BO design, where Ethernet bridging occurs between the leaf devices through VXLAN tunnels being formed between each leaf device. However, inter-VLAN traffic is not required to leave the fabric. Routing occurs at the leaf devices, which function as the Layer 3 VXLAN gateways. These leaf devices have IRB interfaces that route the traffic between VLANs, which enables better resource utilization and lower latency for east-west traffic than the BO and CRB designs. The ERB design provides better convergence, higher scaling, and lower latency than the CRB design, but the configuration of the ERB design is more complicated than the CRB design. However, ERB is the recommended data center fabric design because of its better efficiency over other designs. Module. By the end of this module, you should be able to describe centrally routed bridging. This example shows the data flow when deploying a centrally routed bridging or CRB design. With central routing or enabling a distributed Layer 3 virtual extensible LAN or VXLAN gateway, devices can use the help of either Type 2 or Type 5 Ethernet VPN or EVPN route advertisements. In CRB, the first hop IP gateway address is in the spine. This design centralizes tenant IP management. It also places the higher processing requirements on fewer devices than if routing was done at the leaf level. If most of the inter-VLAN or VXLAN traffic is to and from outside the fabric, the routing mechanism is in line with normal traffic flow if the spine devices are directly connected to the external routing devices. You can refer to the Juniper Pathfinder website for the current list of devices that support CRB. You can access the link from the reference links document in the resources section. The EVPN-VXLAN topology is designed as a CRB design. Leaf devices operate as Layer 2 gateways only. The Layer 3 gateways are configured as distributed gateways on the spine nodes. The spine nodes are also configured as Layer 2 gateways, virtual tunnel endpoints or VTEPs, and as distributed Layer 3 gateways using integrated routing and bridging or IRB interfaces within the Layer 2 domains. The resulting topology creates a full mesh of VXLAN tunnels within the data center. Layer 2 traffic between hosts that are connected to different VTEPs will traverse the VXLAN tunnels between the Layer 2 gateways. The Type 2 route has a very simple purpose, which is to advertise MAC addresses. Optionally, this route can advertise a MAC address as usual, but also an IP address that is bound to that MAC address, which helps populate the Address Resolution Protocol or ARP table in the central routing use case. A leaf device learns MAC addresses in the data plane from the Ethernet frames received. Once the leaf learns a MAC address, it automatically advertises it to a remote device and attaches a target community. Upon receiving the route, Spine 1 and Spine 2 must determine whether they should keep the route. The spine devices make this decision based on the received VRF target community. Traffic between VLANs is forwarded to the spine devices through a VXLAN tunnel. The spine devices route the traffic to the new Virtual Network Identifier or VNI and forward it to the destination VTEP in the destination VNI. The remote VTEPs decapsulate the traffic and forward it to the host. The Layer 2 gateway functions are performed on each leaf device. A VXLAN environment requires BGP peering between fabric devices. With internal BGP or IBGP, you can either implement a full mesh between all fabric devices or peer leaf devices with spine devices that are configured as route reflectors. The centralized route reflector topology is more scalable because as new leaf devices are added, only sessions from the new leaf to the route reflectors are required, which simulates an external BGP or EBGP implementation. Using IBGP for the overlay in a CRB environment adheres to the Juniper validated design. An alternative to a full mesh topology requires that every leaf node in the network creates an IBGP session with the newly added leaf. If you use EBGP as the peering method, each device uses the same autonomous system number or AS number used in the underlay EBGP and requires each leaf to peer with each spine. Layer 3 gateways are on the spine devices, and therefore the Layer 3 routing functions do not change as more leaf devices are added. The only exception is when new spine devices are added. One downside to this topology is that it requires all inter-VLAN traffic within the data center to pass through the spine nodes. As new leaf devices are added, the IBGP signaling automatically advertises the new leaf and new VTEP to the devices within the VXLAN, and new VXLAN tunnels are automatically created.